Okay, now we're going to take a look at solving quadratic equations by factoring and completing the square, something most of you are probably acquainted with. I'm going to start with a somewhat more challenging example with a bit more going on. It can help see patterns maybe a little bit better. And then we'll take a look at simpler or special cases where you can use the same method or you can do them in another way, and then completing the square. So in all polynomial equations, we're going to start by making them equal 0. That's a great way to go. So I'm going to pull these over here to make things positive, especially the leading coefficient. So I'm going to add 8 and 4x to both sides. That will become 0. And when I add 8 and 4x over here, they will combine with the like terms. And what I'm going to do to factor is I'm looking for the two numbers that multiply to 3 times 8, so 24, and add to 14. The reason being is if you think of expanding, which is the opposite of this, and FOIL, you might have heard of, first, outer, inner, last, those outer and inner often terms combine. They're both the terms in X if you have it in the most common way. There are different ways to factor. I'm going to use the box method. Okay, so this box of 2 by 2 is telling me that I have a binomial, so 2 terms times 2 terms that I'm looking for in the factorization, and they will combine to give an unsimplified 4 terms, or when I combine them, these 3, this trinomial. So 3 times 8 is 24. I'm looking for 2 things that multiply to 24 and add to 14. And you can think through all of the different pairs that multiply to 24, like 1 and 24, but that won't add to 14. I'm not going to find all of them. If you had negatives, you would need to consider how these would interact. In this case, I know, though, that if I have 12 and 2, I don't need to keep looking. 12 times 2 is 24, and 12 plus 2 is 14. So those are going to be my x terms that would combine to give me the 14x. So I will put 3x squared and 8. Those terms is like the first and the last. Don't combine with anything. And 12x and 2x. And it doesn't matter which of those boxes they go in. And now what I'm going to do is look at each row and each column and find the greatest common factor. So in the first row, I can divide both of these by x. The greatest common factor of those is x. Here, 4. There's no x I can pull out, but I can divide both of those by 4. I can take 3x out of both of those and just a 2 out of these. So these are my factors. If there's no minus, then it's plus. You're always going to look at the closest box. In this case, the closest box is positive, 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 and positive. If we had had something that was like a negative here, then I may have negatives, and then I'd have to pick negatives. But this is saying that this equals 3x plus 2 times x plus 4. And that still equals 0. This is just the factorization of my trinomial. Now, because anything times 0 equals 0, I can say, okay, well, in one case, what if this equals 0? And if that equals 0, it doesn't even matter what that is. Multiplying it will still give 0. So one solution is x equals -4. And when will this equal 0? I can solve that also as a linear equation. Subtract 2, divide by 3, -2/3. So those would be my 2 solutions. Here are some actually simpler special cases, but the same idea. There's an invisible 1 here. If I'm using the box method, 1 times 5 is 5. I'm looking for 2 things that multiply to 5 and add to 6. Okay, so 5. And if I have those, well, 1 times 5 is 5, and 1 plus 5 is 6. So I have 1x and 5x. And the greatest common factor is 5x. And the reason this is so much easier is because you don't have a coefficient of x squared other than 1. The coefficient is just 1. You really only need to think, well, what 2 things multiply to 5 and add to 6? And that's 1 and 5. And you see those right there. There's not a greatest common factor that gets pulled out. Making each factor equal 0 will give us these 2 solutions of x equals -5 and x equals -1. Okay, here's another one. There's no greatest common factor in here. Getting smaller with my boxes, I need to be careful. 4x squared, 25. 4 times 25 is 100, and I'm looking for two things that multiply to 100 and add to negative 20. And negative 10 times negative 10 is 100 positive, and negative 10 plus negative 10. I'll make the boxes bigger. That's quite difficult to see. Negative 10 plus negative 10 is negative 20. So here's an example of where those negatives will come into play. So 4x squared and 25. These already all equal 0, so I don't have to move anything over. I'm not focusing on that right now. And then we take out the greatest common factors. I can divide both of those by 2 and x, both of those by 5. I can divide both of those by 2x, and this is also 5. And we take the sign of the closest box. So that closest box is negative. That one is negative. And what we see here is that this is actually a perfect square, because anything times itself is equal to a square. So we have the same root twice, and if you were to make this equal 0, we get that add 5 divided by 2. There's only one distinct root. You may remember this, though, with the binomial theorem, where if this is a perfect square, you're going to see this again in a second. And this is a perfect square, so 2x squared is 4x squared, and 5 squared is this. And then if this is double the product of those, then you have a perfect square, and you can just factor those like this. This term can be positive or negative, and it will carry right over. We have another example here that's a special case. Okay, x squared here. This is a nice easy one. We don't actually need the box method because there's a 1 there, but there's actually a 0x in here. So what two things multiply to negative 9 and add to 0? Well, negative 3 and positive 3. Doesn't matter which box we put it in. Those are our x terms. And as we pull out the greatest common factor and pick the sign that's closest, x plus 3, x minus 3 equals 0. Okay, and x equals negative 3. Technically the other way around. And this is the difference of squares. So in these cases, where you have something that's one of those nice binomial theorems or something else you might have learned separately, you don't need one of these methods, but you can still always apply this method. If this is not possible, or if you'd like to do it a different way, there's also completing the square. And this is the same as putting it into vertex form. If you want to look at it like that, those are the steps that you do to convert it into vertex form, which you've probably seen before. You can pause and think through it. But what's nice is once you have it here, it's pretty simple to solve. There's only one variable, one x. And if you're actually using it to solve and not graph and put it in vertex form, you can really just move things over and divide instead of factoring and keeping them there. Okay, so you could just divide both sides by a, and if one side equals 0, then that goes away on the one side. It makes it much simpler, and you can move c over that constant instead of dealing with it. So I'm going to do this particular one, whereas if I just converted it to vertex form and not moved it over, and then in a second I'll show you, like, okay, let's just solve the equation. You can see in this this trinomial we can't factor it because there's no two numbers, no two integers that multiply to negative 1 and add to negative 6. So factoring isn't a method we can do here. But what we can do is say, let's just pretend that I have this so far. What would make it a perfect square? And I could divide this by 2. This is always divide by 2 and then square it. Dividing negative 6 by 2 gives us negative 3, and squaring that is positive 9. But of course, you can't just add 9 to your equation. That would actually change the equation. What you can add is 0. Adding a 0, no matter how you write it, is fine. That's our identity. So plus 9 minus 9 is 0, and we haven't actually changed it. We've just changed how it looks. And now you have a perfect square. Thinking back to what I showed on the last one. And then you can also combine these. So you now have this in vertex form. If you were to graph this, the vertex would be at 310, not stretched, not reflected or anything. But what's nice is you have just one x, and you can follow the order of operations to solve for x. So I'm going to add 10 to both sides. I'm going to take the square root of both sides. Here's my steps. Square root of both sides so that I get into into my parentheses. We do have plus or minus. If we're solving it, if we were graphing it, it wouldn't be a function anymore. That's not a perfect square, so I'm just going to leave it like this. And then the last step will be to get epsilon to add 3. So 3 plus or minus square root of 10. So this is a great method. It's a little bit more work if you can't factor, but it's not too terrible if x equals 1, or the coefficient of x squared equals 1. When you have something like this, it gets a little bit messier, and I'm not going to convert it to vertex form. I'm just going to divide, move things over, and make it as easy as possible. I do see my constant is already on the other side. You could make it equal to 0 as kind of a consistency, but it doesn't matter. And I'm going to divide both sides by -2. And as long as I do it to both sides, I'm fine. Okay, I'm not breaking any laws here. What this gives me is something I can relatively easily put into a completed square, whether this is a perfect square. Divide the coefficient of x by 2, it's -4, and square that as 16. But again, I can't throw this out of balance, so you could either subtract 16 from the side or say, I'm keeping the balance by also adding 16 over here. Those are both the same ideas as the last way. You just have to make sure that what you're adding is equivalent and you're not changing what the actual equation is worth. This is now a perfect square. And this is 16 minus 2.5, so 13.5. And now as you take these square roots, okay, it's not going to be nice plus or minus. Doesn't matter if you put it in as a fraction or a decimal here, and then add 4. Okay, you're still getting something that's not terrible to do. Those are two solutions, plus this or minus this. So we took something that wasn't really factorable and turned it into our solution here.